For the record, I'm aware that that is a horrible drawing of a car. You don't need to point it out. It's a junker. Car like I drive. It's on a 12-degree incline. Okay? The car weighs 3,200 pounds. Find the force required to keep it from rolling down the hill. So let's just think, for example, okay? All right, so we've got Paige. Paige is like, oh no, the car is going to roll down the hill. And so she steps on up, she's going to take one from the team, and she's going to apply some pressure against the car. Okay? Is she able to keep that car from rolling down the hill? What do you think? She is very strong. How many pounds of force do you think it would be required in order to keep that car from rolling down the hill? 50 pounds of force? 100? 300? 1,000? We want to take a guess? A couple thousand? 10. At least 10. Okay? Well, it's a good question, right? Because at the end of the day, whether or not the person can hold it is one question, but you know, they make these things called, you know, like chucks for wheels where you're trying to keep things from rolling down. It's like, what is the force required? When they design this stuff, those are things they have to think about. So what is the amount of force required? And we can figure this out using our information about vectors. So we have this force that is applied towards the center of the Earth via gravity that determines our weight, and that has a magnitude of 3,200. There are also two other vectors for components to this vector that we can draw. One is the red vector, and that is this vertical component here is the weight felt by the driveway. And then you have this green component here, and that is force to keep it from rolling backward. So you have 3,200, and it's made of two components. One, the force required to keep it from moving backward, and the other one, the force exerted against the driveway. Everybody see that? So we've got this number here, and this horizontal component is what we want to find, that force to keep it from rolling backward. What we need is we need an angle for this triangle. So go ahead, take 45 seconds, talk with the peer next to you, see if you can figure out another angle for this triangle. Go ahead, go, talk, go. Okay, 5, 4, 3, 2, 1. If you notice here, okay, you have a couple triangles. We have this small one right here, but we also have this larger one right here, don't we? So if this is 12 degrees and this is 90 degrees, isn't this angle right here 78 degrees? And so if I flip this triangle upright, you can see that that part is 3,200. I have this green portion, which we'll say the 78-degree angle. That's the force required to keep it from moving backwards. And then we have this red part, which is the force exerted against the driveway. So these are, turn the triangle around, okay? And so we have two components to this vector. We have A and we have B. I would like to find component A. What is the formula for finding component A, or the horizontal component of the vector? Close? Yeah, the magnitude of the vector times the cosine of theta. So 3,200 times the cosine of 78 degrees. And B is going to be, and it doesn't ask for it, but we're going to find it anyway, 3,200 times the sine of theta. So horizontal is cosine, vertical is sine. So we take out our calculator, we turn it on, and we type in 3,200 times the cosine of 78, and we find out that Paige would have to exert forth 665.32 pounds of force in order to keep it from moving down the driveway. Paige is strong. Is she that strong? Probably not. She would try to push, it would start to topple her over, and then she would be like lying sideways underneath the wheel, and maybe at that point it would stop it, right? But like, Pato, you're exerting 665 pounds of force. What's your bench? That ain't 665. That's like less than half. You're getting rolled over, buddy. Okay? Get my point? All right. And then the other one, what's the force felt against the driveway? Well, let's take that 3,200 and we'll multiply by sine of 78. And you can see the driveway is feeling a force of 3,130 pounds. So the driveway doesn't feel the full 3,200, but it feels a good portion of it. Okay? Feels a good portion. You good? Okay. All right. Last example then. You're going to flip back in your notes to this part where it talks about a pilot heading west. For the sake of the problem, we're going to say the pilot is not heading west, but rather heading east. And there's a wind blowing at north 20 degrees east, not west. I'm just trying to get this a little bit better. Right here. Okay, so plane, pilot's headed east. Plane's going at 450 miles an hour relative to the air. But the wind's blowing at a speed of north 20 degrees east at a speed of 60 miles an hour. What we want to do is we want to try to figure out kind of the true speed of this jet. Now, I hope you guys understand. Anybody ever been waiting for somebody to come home on a plane? You know, like look like, okay, what's the estimated time of arrival? You watch it change and adjust. A couple of people have done that, but not a lot. Okay, so you know, as you try to figure out, I mean, managing air traffic is an important element of our infrastructure, is it not? Air traffic controllers have one of the most demanding jobs in the world. Okay, very, very stressful. Okay, but part of the calculation that goes into effect is this piece, because if the plane is traveling at say 500 miles an hour and it has a tailwind of 50 miles an hour, it's actually traveling at 550 miles an hour. Okay, that's what's happening. So even though it says 500, it's relative to the air around it. So if the air is moving as well, it's 550. Think about the other example. I'm driving home last night. I'm traveling 70 miles an hour on the freeway. Okay? The wind behind me was a south wind yesterday. It's blowing at 20 miles an hour. Is the cop actually going to stop me and say, hey, you're going 90? He's not. Because I'm going 70 miles an hour, not relative to the air. I'm going 70 miles an hour relative to the ground, right? The ground isn't moving. But when you're in a plane, the air is moving, right? See the difference? So it makes it more complicated. Now, when I'm going 70 miles an hour, I got the 20 mile an hour wind, it does make my fuel efficiency better, right? I have less force that's required of my car to make it go that 70 miles an hour. So that's a good thing. So this is what we're trying to think through. And we're going to take it step by step, and we're going to do the easiest part first, which is part B. It says, express the velocity of the jet relative to the air as a vector in component form. So all I do is I mark off the direction of the jet and its speed. It's headed straight east, and it's going at 450 miles an hour. Now, in the example problem, or the problem you have today in your homework, it's not going straight east, okay? It's headed at an angle. And so you need to make a slight change there, but you'll notice that as it comes up in the wind part here. So the true velocity right now, the velocity of this jet in vector form, okay? There is a horizontal component and a vertical component to the vector I just drew. What is the horizontal component? 450. What is the vertical component? Everybody see that that's nice and simple? Okay. Now let's do the one slightly more challenging. It says that the wind is blowing at north 20. So I'm going to draw a vector here, and I'm going to go where this is a 20-degree angle right there. And it says that it's blowing a speed of 60 miles an hour. 60 miles an hour. Okay. So I'm going to draw a triangle for this one, and then you would have to, in your homework, you would have to draw triangles for both of these, okay? But we know that the vector for the wind has a magnitude of 60. Anybody know what that angle is right there? Close, close, close. If this is 20, then this is 70. Okay, so we're going to go 70 degrees right here. So now that I have this triangle drawn, I want to figure out the horizontal and vertical components. Well, we've already done that with the other problem. A is equal to the magnitude of the vector times cosine of 70, and B is equal to the magnitude of the vector times the sine of 70. So I'll compute those into vector form. Take out my calculator, press on, and I press 60 times the cosine of 70, and I get 20.52. And then I take 60 times the sine of 70, and I get 56.38. This is the vector of the wind. This is the vector of the plane. Is the wind helping the plane move faster? A little bit. Think. The plane is wanting to move east. Does it have an east value that's helping it? Yeah, it does. It's got 20.52. Okay. So the true velocity of the jet is actually these two added together. So you have to understand that when we looked at what happens when two vectors act upon each other, well, you get the result of one being added onto the other. So you can see that its velocity is greater than the 450, okay? Greater than the 450. So as we add these, we simply get 470.52, and we get 56.38. Now, Ray is asking me, hey, Mr. Gantz, how fast is that plane going? I said, oh, well, Ray, the plane is going at a vector component of 470.52 in the horizontal and a 56.38 in the vertical. You're like, Mr. Gantz, just please give me the miles per hour, right? And that's what we want to do. This is the aha moment. Some of you will get it, some of you will not. Speed and velocity are similar, but they are a little bit different. Velocity is a rate of change like speed. The difference is this. Right now, I'm headed in this direction. My velocity is positive, say positive 5 miles an hour. As I'm going this way, I'm negative 5 miles an hour. Velocity has direction. Speed doesn't have direction, right? Okay, but velocity does. We assign value to it. So we say that speed is the absolute value of your velocity. Have we seen that symbol come up in our work over the past couple weeks? So what do we do to find the absolute value of 470.52, 56.38? What do we do to determine that? Do you remember? Square root a squared plus b squared, right? That means the magnitude of that vector. So that's what we're going to do. We have the square root of 470.52 squared plus 56.38 squared. I will compute that, and that will give me that true speed. Hey, little buddy. How we doing? She's not the tallest person in the room. But she has the best smile. She's in my flex. Kind of developed that flex connection here, I mean. I wish our flex group could have been out there doing the Hungry Hippo thing. I think we would have been good at it. It was furry lobster. That was our hangout during Pictionary. Oh well. We get 473.89 miles per hour. So this is important. the wind, the jet is going at 450 miles an hour, but with that 60-mile-an-hour wind at that angle, its true speed is 473.89. I mean, don't you think that that's important information? It is. Okay, and there are ways to figure it out. The last thing we need to do is determine the direction. Because is this plane going straight east? Heck no, it's being blown off course a little bit, isn't it? So here's what we have. We have this is the true direction, where this is theta, and we know that we have a horizontal component of 470.52, and we know we have a vertical component of 56.38. Does anybody out there have a way for me to come up with theta? Hint, we've done it many times before. Yes. What? Tangent. Tangent of theta is equal to what? Field rate, 56.38 divided by 470.52. .473 is the hypotenuse. See it? No? So we go back to this. This is our horizontal. This is our vertical. This hypotenuse here is the 473. Okay? We tangent inverse the 56.38 divided by 470.52. We get a grand total of 6.83. So that is exactly my true direction, because we would say that we were traveling in the northeast direction. And how many degrees do we turn to the east? Not 6.83, but yeah, 83.17 degrees to the east. That's my true direction. Yep. So that finishes off anything that you guys would need to be able to answer any questions on your worksheets. Answer keys are posted. You've got about a dozen minutes. I'll be happy to answer some questions. And you've got some time to be able to work in the other next week. Note, again, that your test is on Thursday. And also note that you will have something else to do on Tuesday in class. That Tuesday's not going to be a full work day. We got some other things to do. Okay.